Okay, good afternoon everybody. I hope you're all keeping well and having a good Sunday. This is the fourth lecture in the epidemiology series. So we've been covering study designs, how to measure error, and basic introduction to epidemiology. And today I'm going to be giving you an introduction to biostatistics. So statistics are obviously quite a crucial part of the research process, because once you've collected your data through the different study designs that we've spoken about, you need to know how to organize and analyze data so that you can start to make sense of what you've found, and also start to try and find out are there associations between particular exposures and particular outcomes. And really this is the core of research, is the application of statistics to data to try and draw conclusions that you can then act on. And they might be related to treatments, they might be related to just defining risk factors. So yeah, so statistics, it's quite obviously a massive field on its own, and usually epidemiologists and public health specialists work with biostatisticians who exclusively have trained in statistics, which is quite necessary because it is quite a complex field. But from your perspective, it's important to have a basic understanding of statistics so that you're able to interact effectively with biostatisticians, and also so that you're able to design your studies properly and calculate the correct sample sizes. And also when you're reading journal articles, if you don't understand the basics of statistics, it's very difficult to understand how valid any kind of results are that you read about, and also to know what to look for when you're reading a journal article, and particularly when you're looking at the tables of statistics. So today's lecture is really just meant to give you an overview of statistics, how you think about it and approach it, but it's not in any way meant to be comprehensive, because this is quite a massive and complex field. So here's an overview of what we're going to be looking at today. So I'm going to start off really right at the beginning to look at what is statistics, what is this, what does it refer to? And then we're going to look at the two main types of statistics, descriptive and inferential statistics. And then under each of those, you can see there's various topics that we're going to cover. So starting at the beginning, what actually is statistics? Well, in any kind of study, as you saw last time when we spoke about study designs, you start off with a population from which you take a sample. And so that's the process that we take, and so we end up with a smaller sample from the population that we've taken. And obviously this now requires us to think quite carefully and in mathematical terms about, how accurate are our results when we're only sampling a small percentage of people from a massive population. So here you can see, for example, let's say the blue dots are people who are healthy, the red dots are people with our disease or outcome. And you can see in our population, we've got a 43% incidence or prevalence of that particular disease. And if we had to take samples of only 6 people from that population, you can see that in these different samples, in the first instance, we have a prevalence of 50%, in the second, a prevalence of 33%, and in the third, a prevalence of 66%. We average all of those out, we reach a prevalence of 50%. So you can see that that already it's not a very accurate way of measuring data, but we're forced to do this, and so we need to use statistics to enable us to get to the most accurate figure. So this brings us to the discussion of what are parameters and what are statistics. So the parameter is really the population prevalence in this situation of any particular variable, and then the statistic is basically what we calculate from our samples. So the 3 ones at the top, those are examples of statistics because they're taken from a sample, and then the 42% at the bottom is the parameter, which is essentially the value in the actual population. Okay, so a parameter, as I said, refers to a characteristic of the entire population, and the statistic is a characteristic of the sample that we measure. So here is just another way of thinking about it. So basically from our population, we take the sample, we get a statistic, and then from the statistics, we actually infer the parameter, because you can imagine in any study, it's not as though you know what the prevalence is in the population. So we use statistics to infer the parameters. So we need to think about how representative our sample is to the population. And when we sample, Of course, our statistics don't equal the population statistics, and this gives rise to what we call sampling error, which we'll go into in a bit more detail further on. And a different sample statistics from the same population can yield different estimates, as I showed you in that example. And so one way of doing that is to repeat your sample several times, and then one starts to then get closer to the actual value of the population parameter. But normally in a study we don't do repeated samples, rather we calculate how we can get a big enough sample size to get as close enough to the population parameter as possible. And I'll go through with you in a moment how one goes about that. So there are two broad areas of statistics. The first is descriptive statistics. And in this type of statistics, we're really describing the data that we've got from our sample. So often it's numerical, and then of course you can display it graphically or in tables. And then we have inferential statistics. And inferential statistics is when we use our sample to infer conclusions. So in other words, we start to say, okay, well, if this is the prevalence in the sample, then this is the prevalence we can estimate in our population. So that's an inference. And then we also look at, is there any relationship between two variables, such as an exposure and an outcome? And we're going to go through both of those in detail as we go through the lecture. So descriptive statistics deal with the enumeration, organization, and graphical representation of data from a sample. And inferential statistics, we deal with reaching conclusions from incomplete information, which would be from our sample. That is to generalize from our specific sample. So in inferential statistics, we use available information to draw inferences. So we know that just in terms of the word infer from English, really inferring something is trying to draw a conclusion from incomplete information. So let's have a look now at descriptive statistics. So if you have any kind of variable, you would want to know the magnitude of that variable, as well as how much does it vary within a population. So let's think of an example. Let's say, as our study, we wanted to find out what is the blood pressure of adults living in Tokyo. So here we would want to know, obviously you're going to get different blood pressures across each person in your population. So we want to know, well, what's the average? So what's the size of the average? And then we'd also want to know, well, how much is the variation? Let's say we have an average of 160/90, but do most people have that blood pressure, or is there a lot of people who have really high blood pressure and another lot that have really low blood pressure? And that's where the spread becomes quite important, because you need to know what is the range of blood pressure in different parts of your population. So let's have a look at some of the measures of central tendency or magnitude. Okay, so one of the commonest ones that you'll have heard about many times, I'm sure, is the mean. And the mean is also called the average. So here, you can see in the picture I've put here, this is quite a simple measure of central tendency, where basically you just add up all of the values and then you divide it by the total number of values. So we can see here that you've got 1, 2, 3, 4, 5, 6, 7 values. They all add up to 32, so we divide that by 7, and that gives us a mean value of 4.57. So this is one of the most widely used measures of central tendency. It uses all the data, because you can see every value in our database is being used. But the one problem with it is that it's very susceptible to outliers. So if we look at this example here, imagine now that one person has a score of 20 or 40 even. You can see that by using this method, we're going to have a very high average, which doesn't really represent the spread of numbers in that population. So the mean is really very susceptible to outliers, and that's why we also have other measures of central tendency that we can use when we have a lot of outliers. So one of these that we can use is called the median. So the median doesn't use every single data point. What it does is that first you order all of your data points numerically, so you can see it goes up chronologically from 2, 3, 5, 7, 8. And then what we do is we find what is the central or the middle value. And here you can see very clearly that it's 5. And so here we would say the median is 5. So you can imagine now again, if we have that person who had a value of 40, we would still have a median of 5. And so in this way, the median is quite resistant to outliers. Okay, another measure of central tendency that also is resistant to outliers is the mode. So the mode now refers to what is the most frequent value, okay? And so in this data state, we have 2 2s and 2 5s, but only 1 3, 1 7, and 1 8. So in this situation, we in fact have 2 modes. So one might even call it a bimodal distribution, where you would have 2 and 5 as the mode. And it can be that there might be no mode if every single value is different. So the mode is oftentimes not just one value, but it gives us a sense of what is the most commonly occurring value. And it's often used for categorical data. So here's an example where people were trying to find out in a particular neighborhood what types of transport do people use. And you can see some people used cars, others trains, trams, buses. And so in order to explain this data to your audience, the mode becomes quite helpful because the mode shows us what is the commonest form of transport, which is buses. So here, you know, medians so medians wouldn't really be a good way of describing this because we're really interested in communicating this information to know what is the commonest form of transport so one could plan around that. Okay, then we have a look at, okay, so within this data set and within this population, how are these values spread across the people? So one of the commonest ways of describing spread or measures of variability is range. So the range is basically your difference between the lowest and the highest value. So here in the same data set, you can see they've all been ordered according to size, from the smallest to the largest. And our range is simply the highest value minus the lowest. And so in this example, it gives us 6. So it's very easy to compute. And again, it doesn't use all the data. And so, yeah, in some way it can be resistant to outliers, but obviously if we had an example of 40, it would be hard to interpret this because then we would have 40 minus 2, which would be 38, and that doesn't really give us a good idea. That is the range in that population, but if everybody is within the range of 8 to 2 and somebody has a 40, it's not really giving us a good sense of what is happening in the population, because we might presume, oh, well, there's lots of people who would have a score between 8 and 40, whereas in reality it might just be that one person. So again, we have different ways of measuring variability or spread depending on how the data is distributed. So one of these ways is to calculate the standard deviation or simple sample variance. And so here are the formula for these calculations. Normally it's done within statistical programs and it wouldn't really be something you would calculate by hand, but it's good to know the formulas in case you ever stuck in the rural area without a computer or a biostatistician. So this measure of spread is called variance. It uses all of the data and it measures the average distance of values from a reference point. Okay, so first of all you would start by finding the mean of all the scores, and then you would find out how much each value deviates from that mean. So that's the reference point that they're talking about over here. So you square all of those values, making them all positive, and then you ascertain the value, which is the variance. So let's have a look what that looks like. So here you've got a normally distributed data set. Here is our mean score, and then each of these is a standard deviation. So this tells you how far away from the middle score is that range of data deviating. So that's 1 standard deviation, 2, minus 1, minus 2. Okay, so then the other aspect of descriptive statistics is also not just to write down figures in terms of, you know, means and modes and range, but also to actually display the data to your audience so that they can really have a better understanding of what it is that you're seeing in the population. We don't have time in this lecture to go through all the different kinds of displays, but one of the most basic is the scatter plot, where you would have X on one side and Y on the other side, and then you would plot your variables depending on what they are. And then very often, I'll show you a little bit later on, you would incorporate the scatter with the line graph, where you then calculate, okay, is there any kind of relationship, and then you demonstrate that with a line. But depending on your data, you might prefer to use pie charts, bar graphs, histograms, there's really an endless ways in which data can be displayed. And what's important to think about is what is the easiest and simplest way to display your data so that your audience can actually comprehend what you're trying to communicate. Okay, then I just wanted to mention a little bit about the distribution of data. So remember we spoke a little bit earlier about outliers. So if you have a lot of outliers, it can actually skew your entire data pattern. So the data pattern that we like best and actually describes most of characteristics in humans is the normal distribution. So here you have a median and you have roughly equal amounts of data on each side of the median. Okay, and in a normal distribution, the mean equals the median and equals the mode. So the commonest occurring value is also the middle value and is also the average of all the values. So you can see it's symmetrical. So here data is symmetrical on either side of your median, mode, or mean. Okay, but you can also have data where you have a lot of outliers on one side, in this case positively skewed, or on another side, which would be called negatively skewed. And it's important to know this because this determines which value, either the median, mode, or mean that you're going to select, which measure of spread, but also, as you'll see a little bit later, it also determines which statistical tests you can actually apply to your data. And in fact, in many instances, because it can be difficult to analyze skewed data, we often use other statistical methods to convert the data to become normally just distributed, oftentimes by doing a log function of that data. So if we think now about what kind of data that we're going to be dealing with, we've already spoken about the fact that you get numerical data or categorical data. So numerical data is obviously your count data, so it would be numbers, and then categorical data would be like our example with transport, bus, train, tram, or in disease states it's often has disease, doesn't have disease, exposed to risk factor, not exposed. So categories are not numerical. They're very oftentimes binary, but they can also be ordinal, where you might have mild disease, moderate disease, severe disease. So you have different categories that go up in a particular order. So when we have these two different types of data, we apply different statistical tests to them. So it's important right at the beginning to think about what sort of data is this, and then to apply the correct ways of measuring and describing that data. Okay, so now we come to inferential statistics. And as I said before, inferential statistics we use to infer conclusions from a sample. So you can only use inferential statistics to draw conclusions about an entire population if you have a complete list of members of the population from which you draw a random sample, and then using a pre-established formula, which we're going to have a look at, you determine that actually your sample size is large enough for you to draw conclusions about that population. So let's begin then with looking at sample size, because this is one of the most important factors in having statistics that you can actually infer conclusions that are accurate. So let's say, for example, we wanted to estimate the proportion of South Africans who have COPD, chronic obstructive pulmonary disease. And from the literature, and maybe small studies in the country, we think it will be about 12%. And then we decide we would like a 95% confidence interval that our estimate is accurate within 2%. So in other words, if we think it's 12%, we want to know that when we do our sample and we calculate our statistics, that we would get a result between 10 and 14%. So what does this 95% confidence interval refer to? Okay, so as I said to you before, we take a random sample from our population and then we measure a statistic. So we can imagine the true proportion of, let's say, COPD in South Africa. We call that P, large P. Our estimated proportion would be small p, okay? So how likely is it that our estimated proportion is exactly equal to the true value in the population? So how likely is it that small p is exactly equal to large P? So the range of our plausible values of our sample in which the true population is likely to fall 95 times out of 100 is what we call the 95% confidence interval. So what does that mean? What it means is that if I take a sample from our population, then 95 times, if I take 100 samples, then 95 times the value that I will get from those samples would actually be equal to the value in the entire population. And obviously you can imagine that the larger the sample size, the better and the smaller our 95% confidence interval will be. So if you have a very small sample size, we would never be able to get a range of just plus or minus 2% on either side of the 12. It would probably be more likely plus or minus 10%. And that's why you need to find out what sample size do you need to get something that's actually meaningful. Because if it's going to be plus or minus 10%, you can see already you can get an estimate that might be almost zero, which is not going to be accurate or helpful at all. So sample size is critical to try and help us get a narrow enough confidence interval that will help us determine our estimate. So coming back to our example, what we would do to calculate this value is we would go to Epidata or Epistat, StatCalc, EpiInfo, which is freely available, and I've got the link a few slides down. And here you can see you have many options to do tables, chi-square tests. So here you would select sample size and power, and then we would select population survey because that's what we're doing to try and establish the prevalence of COPD. So first you need to fill in, okay, what's the size of the population from which the sample would be selected? And that information you would normally get from the statistical services in your country. You can normally find out exactly the size of a population within the community you want to do your study. Then you need to know the expected frequency of the factor. So remember we said we think from the literature, from local studies, that the local prevalence is 12%. And then you have to plug in here, what is your worst acceptable result? And you could either put it in as the higher level or the lower. And remember we said we wanted plus or minus 2% level of accuracy. So here that you plug in 14. And then you just press enter, and then it tells you what sample size you would need for any particular confidence interval level. So the standard confidence level that people use is 95%. So what this tells us is that from a population of 1.5 million, we would need to sample about 1,000 people in order to give us a point prevalence with plus or minus 2% confidence interval that we can be 95% certain will repeatedly approximate the population parameter. So let's have a look now. Let's say we decided, okay, we don't need it to be so accurate because maybe we don't have the money to go and find 1,000 people. So we say, okay, what if we prepared to accept a plus or minus 4% confidence interval? So here we've changed now worst acceptable results to 16%, which is 12 plus 4. And you can see here at the 95% confidence interval level, we now only need to find 253 people. So this has radically reduced our costs, but it has widened our confidence interval. But, you know, what would our results come out to? It would be 12, so it would be from 16 to, so from 8 to 16%. So that's still quite meaningful. So, you know, you need to decide, is that result going to be good enough? And generally people go for the smallest sample size to give the best result. Okay, so if we think about statistical analysis, we have gone through descriptive types of analyses, and analytical is what we're into now. So analytical and inferential are fairly similar, but you can have univariable analyses, in other words, when there's one variable, like prevalence, for example. But oftentimes it's still inferential because we're still using that information and applying confidence intervals to it to infer information about the population. So this sometimes can also be analytical or inferential. Bivariable refers to when we have two variables, which we're going to look at now, and then multivariable is when we have one or more variables, which we'll look at a little bit later. So a univariable would be an example of prevalence. Bivariable, we might want to know what is the distribution of gender by hypertension status. In other words, is there a relationship between gender and hypertension? And then in multivariable, we might want to know how many different risk factors are able to predict who does or doesn't become hypertensive. So let's have a look now at some bivariable analyses. Okay, so an example now of bivariable analysis would be, let's say we wanted to test the difference between two means or proportions. So it might be, we might want to know, okay, for our adults in Tokyo, do males have higher blood pressure than females? So now we're comparing two different prevalences, so that makes it a bivariable analysis. Or we might want to test for correlations between exposures and outcomes. So it might be, okay, do people who eat a lot of salt, are they more likely to have hypertension? Or are unemployed people more likely to be depressed? So here, some concepts that are important for you to understand in terminology in particular is that we have an independent variable and a dependent variable. So the independent variable can be an exposure, a risk factor, or an intervention. So it's normally something that is going to influence an outcome. And then the dependent variable, its value normally depends on the independent variables, hence it's called dependent. Okay, so this is normally a variable that's static, and then the dependent variable is not static because it's dependent obviously on exposures, risk factors, interventions. So here we now jump back to remember our discussions around causation, where we want to know, is there a cause and effect? But of course, as I explained to you in the previous lectures, there might be a correlation between two events, but doesn't necessarily imply causation. So the statistics that we're talking about today are really just ways of trying to find out, are there correlations or links or associations between variable X and variable 1. You still need to apply the Bradford-Hill criteria that we went through last time to determine whether or not that correlation is causal or not. But as you'll see, the way that we do our statistical analysis will start to help you go through some of those criteria. Okay, so what is the first thing we do once we come to bivariable or multivariable analysis? The first thing you need to do when setting up your study is to do what we call hypothesis testing. So the first thing that you need to do is to state a null hypothesis. So let's say our hypothesis was that men in Tokyo have higher blood pressure than women. The null hypothesis is basically, well, what would that be if it were not true? So in other words, it would be the hypertension in men in Tokyo equals the same amount, the same prevalence of hypertension in females in Tokyo. So in other words, it's the very opposite of what you think you're going to find, okay? Then we state the alternative hypothesis, which is commonly denoted as HA, and that would be, in that example, men in Tokyo have higher blood pressure than women, and then we decide on a suitable statistical test. We're going to go through that, and then we check, are our findings due to chance or not? And we're going to go through each of these in turn. So let's start off with stating our null hypothesis, which is commonly written as capital H and then with a small o next to it. Okay, so as I said, the HO is a null or no effect hypothesis, and then H1 or HA is the research alternative hypothesis. And what we're actually doing in statistics is we're not actually testing that what we think is true, we're testing that what we think is not true, okay? So we only test the null hypothesis. So let's take an example. Let's say we think as researchers that eating apples lowers blood pressure. The null hypothesis would then be apple eaters' blood pressure equals non-apple eaters' blood pressure. Our H1 or alternative hypothesis would be apple eaters' blood pressure is less than non-apple eaters' blood pressure. Okay? Then we need to decide, okay, what kind of statistical test is going to be appropriate to this type of data. So here, we don't have the time to go through every single one of these tests, but basically one of the first things that you need to figure out is what is the nature of your variable. So here we've got categorical. So an example, it might be high blood pressure, low blood pressure might be a dependent variable, and the independent variable would be eats apples, doesn't eat apples. So that's an example of where you have two categorical variables, and then you would use the chi-square test. But as you can see, you can have many different combinations. You could have one categorical variable, which might be does or doesn't eat apples, and then the second variable, we might just want an actual measure of blood pressure, which would be a numerical variable. And then, as I said to you, one of the other important factors to consider when selecting the test is not just what type of data you're using, but also is it normally or not normally distributed. And what I wanted to point out to you here, as you can see, we use very different tests depending on the distribution of the data. So I won't go through all of these, but you'll see all of these tests really appearing in the literature, and these kinds of tests are what your biostatistician can advise you to use. And it's good to really have a conversation with them even at the beginning of designing your study, because depending on what test you're going to use, you might decide you want to make your variable categorical or numerical. So like in our example with blood pressure, you can see that it could be numerical, where you actually measure as your outcome actual blood pressure, or you could very easily make it categorical, where it's low blood pressure, high blood pressure, and normal blood pressure, so you might have 3 categories. And so the way in which you decide to define your data will determine what tests you can use, and therefore also what you can test. All right, so let's then get back to now our process of hypothesis testing. So we've already gone through our hypothesis, we've stated our null, we've stated our alternative, we've selected the most suitable test, and now we need to know, okay, so we've now got our test statistic, which gives us our results, but how do we know how accurate that test statistic is? And that's where the p-value comes in. So let's have a look at that. Okay, so the p-value is something I'm sure you've all seen a lot of in journal articles. And what it is that it's a measure of statistical significance, which tells us what is the probability that this finding that we have in our study is just due to chance. Now, why do we need to think about this? Well, if you think about it, we're sampling from a population. So it's quite possible that through your sampling, you can end up with a finding that's inaccurate, and that's just due to chance, simply because you haven't measured those variables in the entire population. So this is a very important part of statistical analysis. So our p-values, because it's a probability, so probability, as you know, can only range from 0 to 1. So either it's completely unlikely to happen, or it's definitely going to happen. And those ranges would then be 0 to 1, and obviously it can be somewhere in between. So something might be 50% likely to happen, which would be 0.5. So what we use in statistics and in analysis is kind of a random cutoff, where we say that if the p-value is either 0.05 or 0.01, then we regard those values as statistically significant. So now, remember I said what we're testing is the null hypothesis. So we want to be sure that the chances of the null hypothesis occurring are 0. So that's why we take the smallest numbers. It's because we're testing the null hypothesis. If it was the reverse, we would be looking more for numbers approaching 1. Okay, and so any results where the p-value is larger than 0.05, we disregard those results because they could very easily be attributable to chance, and then we conclude that the null hypothesis cannot be rejected. So here's an example from a study. So this study, we were looking at the health belief model, which is basically a model that tries to describe how people make decisions to change their behaviors around health-related changes. So some of the factors that one considers is, does the person, let's say we're trying to find out how do we get more people to go and get tested for TB, all right? And our intervention is we're going to show them a video about TB, which helps them understand that they are at risk for TB, that if they get TB, they're going to die, and then in order to go and be tested, all they have to do is go to the clinic, but then maybe the person feels, well, but then I'm going to have to wait 6 hours in a queue. Maybe there's stigma associated with TB, so I might be seen to be having TB if I go, and then there might be things like, well, actually I've got a full-time job, how am I ever going to get time off to go to the clinic? So those might be the types of thoughts that people have that affect whether or not they're actually going to be tested for TB. So those different thoughts, how susceptible or high risk I am, how serious is the disease, what would be the benefits of being tested, are there any barriers to being tested, and do I actually have the ability to go and be tested? those are some elements that we might want to measure. So in this study, they measured all of those things, and then they tried to find out, okay, which of these ideas is the one that most predicts whether or not the person will, let's say, go and be tested for TB, okay? So here's the odds ratios that they've got. So here, we know that an odds ratio of 1 or more means that they're more likely to do something. Here, a ratio of odds ratio of 1 or less means they're less likely to do something, okay? But now, before we now start going, oh, okay, well, here we go. So this is more than 1, so people who think they're susceptible are more likely to be tested. Actually, if we look at our confidence interval, it ranges from below 1 to above 1. So already this is telling you that this result is not really accurate enough for you to have to draw any kind of conclusion. And you can see the p-value is almost 1. So that means we have almost 0 chance of saying that this result isn't just simply a product of chance. So when we look at this table here, we can see actually there's only 2 results here that are statistically significant, or that we can't say have occurred from chance alone. And those are barriers. So does the person perceive that there's barriers to going to be tested? So what happened in that situation is where people felt there are barriers, let's say waiting in a queue or engaging stigma, they were less likely to go and be tested or change their behavior, and that is a statistically significant finding. The other finding that we can see is significant is those people who felt that they did have the ability to go and be tested were more likely, because the odds ratio is greater than 1, they were more likely to go and be tested, and that's also a statistically significant result. So where somebody is more likely to do something, we say it's a positive association. So there was a positive association between self-efficacy and behavior change. And then where the odds ratio is less than 1, like it was over here with the person's perception of barriers, we say there's a negative association between barriers and likelihood to change behavior. And then we don't even mention these other results here, except to say that we cannot say that these findings are significant, but they could be due to chance. So you can't say that there's definitely these other elements don't have an impact on behavior, but what we know is there's not enough evidence in this particular study to support those kinds of conclusions. Okay, so now we need to think about, okay, so if we're doing bivariate analysis, as I said, we're trying to find associations between certain exposures and certain outcomes, okay? And so if we plot those values on our scatter plot, you land up with a lot of little dots. And then what we can actually do is what we call linear regression, and this is the formula for linear regression, where we use all of our data points from our sample to see what is the relationship between X and Y. We plot it, and then we use linear regression to basically draw a line that can summarize the relationship between X and Y. Why do we do this? Because then we can actually use this formula or algorithm to then start predicting. So here's an example of how we can use it to predict values. So let's say we did a study and then we came up with the least squares line, which is the line that I showed you, that basically gives us a formula for, so on the y-axis we had length, and then on the x-axis we had gestational age, and this is all of babies, okay? So we're comparing length with gestational age and birth weight. So now we want to know, okay, if we have the length and the birth weight, the length and the gestational age, okay, sorry, I'm getting confused. If we have the birth weight and the gestational age, then how do we calculate the length, okay? So here we take our formula, and if you look back at the previous slide, this is the formula that we would have had. And here we can now plug in both of those values so that we can actually start predicting how long a baby would be at 20 weeks or 30 weeks, whatever we want. So if we say that the gestational age is 29 weeks, then we replace X for 29, and then we can work out, okay, so this baby at 29 weeks is going to be round about 36.93 centimeters. When I say round about, it's because we've used a sample. So we then calculate our confidence interval. Here are some of the formulas for confidence intervals. And what we can then work out is that actually that baby would be between 36.4 and 37.49, 45, I think it's centimeters. And that is our 95% confidence interval. So obviously, this has a lot of value in health services to try and predict what particular outcomes are going to be. Okay, so then the other thing we need to think about is looking at some of the errors in hypothesis testing and how we go about correcting that. So remember, HO is the null hypothesis, and what we find is that there can be two different types of errors when we're doing our statistical testing. So this is a way of kind of summarizing how the two main types of errors that occur. So on the left-hand side, we have our test statistics. Okay, so this is what our results of our statistics show. So either it says to us, okay, we can't reject the null hypothesis, or we can reject the null hypothesis. And then, of course, we can compare that to, well, what's the truth, the actual truth in reality? So in reality, if in fact the null hypothesis is true and we reject it, and we do not reject it, then that's correct. If we reject it mistakenly, then we call that a type 1 error. If in reality the null hypothesis is false, in other words, our alternative or research hypothesis is true, and then we get a false positive, then we call that a type 2 error. So we're going to go through these in a bit more detail. And then just to point out that the p-value is the probability of making the type 1 error. Okay, so let's have a look at these in a bit more detail. So type 1 error, in this situation, we reject the null hypothesis when it is in fact true. Okay, so we find an association between two of our variables, such as an exposure and an outcome, but actually there isn't one. So this is what we would call a false positive. And the causes can include bias, confounding, effect modification, and as I said, the p-value is a reflection of the probability of making a type 1 error. So if our p-value is less than 0.05, the probability to make that kind of error is less than 5%. But we also have type 2 errors where we reject the alternative hypothesis, which is our research hypothesis, when it is in fact true. So here we would think of that as a false negative. So we do not find an association between two variables, such as an exposure and outcome, when in fact there really is one. So here it's the same kinds of causes can result in this. But the other factor here is around our sample size. So if our sample size is too small, you can see how it's quite possible that we don't get enough incidences where we've got cases and controls and exposures and not exposed to actually find enough evidence. So sample size is very important, especially in terms of type 2 errors. So let's just have a look at confounding again, because this is quite important when you're trying to avoid both type 1 and type 2 errors, because if you have a confounder and you haven't adjusted for it, you can get either false positives or false negatives. So if you remember back to our previous lectures on confounding, a confounding variable is one where it's a variable that is independently associated with both the disease and the exposure, or both the exposure and the outcome. So you'll remember previously from our example that if we're trying to look at the association between smoking and cardiovascular disease, the coffee drinking is in fact a potential confounder because it would be independently associated probably with cardiovascular disease as a stimulant, it's quite likely, and smokers probably drink more coffee because cigarettes taste terrible. So here we have a possible confounder that could either dilute or exaggerate our findings. So when we went through study design, I explained to you how you would go about trying to prevent confounding in your actual study design, but you can also deal with confounding at the stage of analysis. And there's two ways of doing it. One is stratification and the other one is statistical modeling, and we're going to have a brief look at both of those. So what is stratification? Okay, so let's take this example where we maybe want to have a look at the association between obesity and cardiovascular disease, okay? But it's quite likely that people have a family history of heart disease, that can influence whether or not they develop cardiovascular disease, as we know, and it's also going to influence whether or not they're obese. So we need to really find some way of separating out the people who have this history from those who don't, so that we can see what is the effect of obesity and cardiovascular disease when we remove this confounder. Similarly, there's also going to be independent associations with gender. So the relationship between men and women to both obesity and cardiovascular disease is going to differ. And so as you can see, the way that we stratify is we actually separate out our results according to the potential confounders. And so instead of having exposed, not exposed, disease, not disease, just for the entire group, we separate those results out into these 2-by-2 tables for each of the groups within our stratifications. So when we calculate our odds ratios or relative risks from the 2-by-2 with everybody together, we call that the crude odds ratio or relative risks. And then what we do for confounders is we start calculating the different relative risks or odds ratios for each of those stratums, and then we need to adjust for that, okay? So let's just have a look at how that works. So this method of separating our crude odds ratio into stratums and then using a formula to try and weight the different odds ratios so that it's representative of the different stratums. That method is called the Cochrane-Mansell-Hansel method, and it's quite simple really. What it really is doing is calculating your different odds ratios or relative risks for each stratum, and then it just weights them according to what percentage of that population in our sample has that particular confounder. So here's the formula for it in terms of relative risks. You can look up online. There's lots of examples if you want to see the actual numbers. But it's actually really just a weighted odds ratios over each other. So there's the formulas, and these are the tables that you would be using. And in essence, it allows you to compute a weighted average of the estimates of the risk ratios or odds ratios across the strata. And then when we calculated that, we call that the adjusted odds ratio or relative risk. And so that's what you would use. So now what about if we have multiple outcomes multiple exposures? Okay, so we've gone through univariable, bivariable. Now we need to look at how do we deal with data sets and what statistics can we use, how do we approach data where we've got multiple exposures with one outcome. So remember that this is often the case when we look at causality, that we have multiple exposures that can interact with each other. We spoke about interaction and we spoke about effect modification. And so now we need to have ways of actually trying to analyze this statistically. So just an example to remind you that, for example, with lung cancer, some of the risk factors might be age, smoking, exposure to dust. And then we remember when we had to look at asbestos and smoking, how actually asbestos interacted with smoking in such a way that each amplified the other one's effects, which we called effect modification. So our multivariate analysis enables us to really analyze more than two variables at once. So what we do, we extend our simple model to include more variables, and this allows us to then, much like that example with the length of the baby when related to gestational age and birth weight, we use these models to then predict, okay, so if somebody smokes and they don't do any exercise and they have a genetic predisposition, then their likelihood of getting this disease is X. And you might ask yourself, okay, well, how is that helpful? Well, it's very helpful because it enables you to know, for example, okay, if we reduce the amount of smoking in the population by 50%, then we can actually predict exactly by how much the disease, let's say lung cancer or cardiovascular disease, would be reduced. So these are very important, and it's very important to have predictive algorithms. So this was the model, remember, for our simple linear regression where we have X, and Y, and then we use our data points to draw a line. And then these here refer to the angle and intercepts, basically, of that line. But now we don't just have two variables, X and Y. Now we have more variables, which are typically denoted as X1 and X2. And as you can see, I mean, you can just keep adding, really, okay? So we can line up with quite long formulas. And then we can even add interaction terms. So remember with, we were looking at lung cancer, as I said, smoking and asbestos interacted. When you have variables that interact, they have a multiplicative effect, okay, rather than just the additive effect. And so you can see here that they're actually put in a multiplicative way next to each other as x1, x2 together. So this allows us to incorporate and control for many variables, because as you'll see, this in fact helps us to deal with confounders. And so in this instance, we're looking at a single continuous dependent variable with multiple linear regression, and then we have multiple independent variables, which could be continuous or ordinal. So let's take an example. So here, one of your exposures might be race, and you might want to know how does it impact on, I don't know, it could be anything really, mortality or attendance at a clinic. And then you can see here we've got, let's say, 4 categories of race. So we might make one of them neither x1, 2, or 3. So you've got 0, x1 would be black, x2 Hispanic, x3 Asian. And then this is what the formula would look like that we would create, okay? Okay, so here's an example. We won't go through the details because it doesn't matter, where you can see that this is the formula that they've calculated, so it would have looked something like this. And then they're just plugging in the values now for the different x's, and in that way they can predict. And so here that would have been our intercept, that's your one x, that's your other x, and then they're literally just plugging in values to predict what the outcome would be for those particular values of x. So one of the benefits of this type of regression is to deal with confounding. So as I said, confounding occurs when the effect of a variable distorts both the exposure and the outcome. And so we can actually put in confounders. So let's say the relationship we're interested in is actually just between x and y, but we know that there's another factor, let's say call it x2, that could be confounding. All that we need to do to adjust for it, to see the effect of just x alone, is to add it into our model. So this is a great way of being able to deal with confounding without having to use stratification. So this is quite commonly done in models. But of course, it's important, as remember I said to you in one of the previous lectures, it's important that you've thought about what the confounders are. Because why that's necessary is that A, you need to make sure you've measured for it in your study, and then B, when you're doing your analysis, you need to remember to actually put it into your model so that you can adjust for it. So that's how we would do that. And then, as I mentioned, there might be interactions, such as that between smoking and asbestos exposure. And then what we do with the interactions is we actually can again, just put that into the model to try and remove the interaction effect. Okay, so let's have a look at, in this example, we've got our smoker, our non-smoker, and now we want to remove that interaction effect. And so that's pretty easy to do if we just multiply them together. And then you can, when you're calculating the effect of smoking alone, even if you have some asbestos smokers in your sample, you're still able to predict if somebody just smokes and doesn't use asbestos, so then that would be 0, which cancels out that whole interaction, what the impact on the outcome y would be. And what we find with effect modification, remember that first graph I showed you with simple linear regression, there was just one line, okay? And normally that's the case if there isn't interaction, but with the interaction, you have basically two different lines, those, for example, where there is and there isn't the interaction. And what that really just means is that there's a different algorithm for somebody who just smokes, and there's a different algorithm for the person who does or doesn't smoke. And the reason for that is because when there isn't that interaction, as I said, this value x2 would be 0, so this entire part of your equation falls out. Okay, so it's quite a complex process, building multiple regression models, but basically the first thing that you do is you want to establish which variables are correlated with each other. And so to do that, you start off with your scatter plots. You might do simple linear regression to see, the relationship between two variables. And then once you've done that, then you can start selecting which variables to put into your model. And obviously you want to select the variables that have the strongest correlations, And then once those are in there, then you can start adding variables perhaps with smaller associations. And then obviously, as I said before, you need to think about adding in your confounders. So there's actually different approaches to building models, and there's not time for us to go through it here, but it is something that you can look up, and essentially you can build a model backwards or forwards. There's certain steps that you can take. So depending on what type of data you've got, you might choose different models of different approaches to building your model. But the very basics of it are really defining what are your outcomes, what are your exposures, which variables have the biggest correlations, making sure you put in those first, and adding in your confounders. And then obviously you need to test for things like effect modification. So this example that I've given you around multiple linear regression refers to data where your outcome is a continuous numerical outcome. So that might be height, weight, blood pressure. So in other words, a number that is not either 1 or 0. But of course, there's many examples where your outcome might be a category, such as diseased or not diseased. And so when you have a kind of a binary or categorical dependent variable, you would need to use logistic regression. And the formula is slightly different and a little bit more complicated. But again, it's something that, it's really just about identifying which regression model to use in, for example, status, DPSS, and then it's actually just as easy to interpret as the linear regression. There's also different kinds of regressions depending on the nature of, depending if you're a dependent variable. So we've spoken about a categorical one. Others might be a count. So it might be different stages of cancer. So it could be stage 1, stage 2, stage 3, stage 4. So that would be a count. And then there's also other types. There's many types of different regressions that you do depending on the type of data that is your dependent variable. So in summary, we use statistics to infer information about populations and to predict outcomes. The main features of a measured variable are its central tendency and its spread. And these are measures, and then which measures to use depends on how your data is distributed, okay? So whether it's normal or skewed, and in fact, both of those elements of data, the type of data and whether they're normally or not normally distributed have a big impact on what statistical tests you will actually use and select to use. The other important point was that analytical studies are based on testing the null hypothesis. So it's a little bit counterintuitive because often we think that in research we're testing the research hypothesis, but actually we're testing the null hypothesis. And because of that, we're looking for the lowest p-values possible. So p less than 0.05 at the very least. And then the tests that we use in our analytical statistics depend on the nature of the variables being investigated, whether it is discrete, continuous, categorical, the number of variables, in other words, is it a univariate type of analysis we're doing, or bivariate or multivariate. And then lastly, the study design will determine, do you have odds ratios or relative risks, etc. So as I said, this is just an introduction to statistics. As you can see probably already from this lecture, it's quite a complex field. But I think at this point, it's important just to kind of have a sense of how one would approach it so that you're able to engage by statistical professionals and read journal articles and start calculating your own sample sizes. So thank you very much for your attention, and I'm wishing you all a lovely rest of the Sunday. Thank you.